Welcome back. We left off talking about high mass stars and the evolution of high mass stars and how they can burn all the way up through iron. This is one of my favorite plots to show why that is. So let's take a brief moment to look at what it is we're looking at here. The y-axis is mass per nuclear particle, right? So the total number of the total mass that atom has divided by the number of protons and neutrons in its nucleus. If all protons and neutrons combine to make the same kind of thing, in other words, if they didn't lose any mass when you put them together, all of these would be the same and they would all be a straight line. If protons and neutrons had the same mass, which they have roughly, and putting them together didn't change their mass, this would be a straight line and flat. On the x-axis is atomic mass, number of protons and neutrons. So 1 is hydrogen, 4 is helium, 12 is carbon, 16 is oxygen, iron is 56, uranium's out here in the 240s or something. Anyway, this is basically element number on the x-axis and mass per nuclear particle on the y-axis. And you can see a lot of the things we've been talking about are explained in this one graph. So in going from hydrogen to helium, why do you get energy out? You get energy out because helium has a lower mass per nuclear particle than hydrogen does. You're basically converting mass into energy when you go from hydrogen to helium, and a huge amount of it. Look how much is available to you. Beryllium is up here. It actually takes energy to make beryllium, which is why it doesn't want to happen. The next stable thing to make is lead, or as carbon, but you get a much smaller amount of energy in going from helium to carbon than you did in going from hydrogen to helium. And each successive squeeze of the orange, it's not a bad analogy that I like to use. Making energy from atoms through fusion is like squeezing an orange. Every time you squeeze the orange, you get a little bit less juice out. Almost all of the juice is gone by the time you've gone to helium. You get a little bit more juice out and going to carbon, a little bit more out from oxygen, and these other iron elements up through iron. Iron is the bottom. Once you've gotten to iron, you have squeezed all of the juice out of that orange. There is nothing left to squeeze out. You cannot get any more energy out of fusing iron into anything heavier. In fact, it takes energy to make anything heavier than iron. Iron is the lowest energy state there is. You can't get lower than it. Incidentally, this is why in nuclear power plants on Earth, you can make energy by fission. You take a uranium atom and you turn it into a lead atom. Again, you're moving down, you're turning mass into energy. That's how nuclear power plants on Earth work, turning uranium, say, into lead and other radioactive elements. But that's why it works. Oops, let's go back. That's why it works. In any event, iron is the end. You get energy through fusion going to iron from the bottom, from lower mass elements. You get energy through fission going towards iron and going from higher mass elements. So where are we? We are at the end of a very massive star's life. It has burned silicon into iron. Iron is there. What happens next? Well, this iron core is supported by electron degeneracy, the same pressure that supported a white dwarf and the same pressure that supported a star when it was undergoing helium flashes and helium shell flashes. It turns out that there's a fundamental limit to how massive you can make something that is supported by electron degeneracy. Again, remember when we talked about the Pauli exclusion principle, as you try to squeeze these electrons closer and closer together, it's not that they can't occupy the same place at the same time, it's that if they do, they have to go to a higher energy level. Well, that's okay and fine, as long as you're pushing these electrons closer and closer together, the next one just has to go to a higher energy. Well, what does a higher energy mean? A higher energy means it's moving at a faster speed. It turns out that there is a limit to how fast you can make an electron go. There is a limit to how fast you can make anything go. And that's the speed of light. It's a fundamental limit of the universe. Nothing can move faster than the speed of light. So there comes a point where if you have a ball of electrons and you try to throw one more ball into this, one more electron into this region, it can't be there because all of the states, all of the lower energy states in that particular area are occupied. And to enter there, it would have to be moving faster than the speed of light, and it cannot do that. And there was a very famous, we'll talk more about him later, Indian astrophysicist by the name of Chandrasekhar, perhaps the greatest theoretical astrophysicist of the 20th century, who realized this fact and did a derivation in which he showed that you cannot make something that is more than 1.4 solar masses out of this electron degeneracy. Once you exceed that mass, electrons will have to moving the speed faster than the speed of light, and it just can't happen. So that's the situation in the center of our star. We have an iron core, and the iron atoms are nice, but it's really the electrons that are holding it up from collapse. And once the combined weight of the electrons and iron atoms exceeds 1.4 solar masses, and it will in the centers of these very massive stars, this pressure that has been holding this core up against collapse no longer works. It no longer is effective at holding the core up against collapse. And so something dramatic has to happen. What is that dramatic thing that happens? Well, the core itself, all those electrons go away. The iron atoms photodisintegrate. This is a great word, and it's such a great word that I'm going to actually write it down on my low-tech low-tech whiteboard so you can see it. Photodisintegration. Here we go. You ready? Photodisintegration. Photo really meaning light, disintegration meaning, you know what disintegration means. It means disintegrating atoms by light, and that's basically what happens. The photons that are running around in this soup are so energetic that they start to break apart the iron atoms that form the center of this star. Let's go back to, my PowerPoint slide, and we'll see what. Okay, so the iron atom gets photodisintegrated. Basically, very high energy photons at the center of this star are so energetic now that they can break apart these iron atoms. And all of that work that you did over millions of years to combine hydrogen into helium, and helium into carbon, and carbon into oxygen, and oxygen into neon, and all these other elements is undone in a matter of an instant. All of those hydrogen atoms go away. They get photodisintegrated back down into protons and neutrons, all of them. Now, the electrons have to go away because the electrons are the electron degeneracy was what's holding the star up. And we know that that can't be the case anymore. So what actually happens to the electrons? Let's think about what happens to the electrons. They combine with protons to form neutrons. Let's go back to our whiteboard, and I will show you briefly how this works. Okay, so electrons, I'm going to write this out in equation form, form with protons. They smash into the protons, and they combine to make a neutron. Now, let's think about how we, so we have a one negative charge from the electron, we have one positive charge from the proton, we have no charge from the neutron, so that works. We have a net zero charge on the left, we have a net zero charge on the right. Now, the problem is this electron, and we have the same number of nucleons. We have one proton on the left and one neutron on the left. That's fine. But this electron, remember, carries something that we call lepton number. And so we need to have another particle over here that has a similar number that is going to balance our equation. And this can't have a charge. We know what these things are. We call these things, that's the Greek letter nu. These are neutrinos. So there should be roughly equal numbers of electrons and protons, and virtually all of them go away in this way. The electrons and the protons combine to form neutrons, and you get a sudden burst of neutrinos coming out. Okay. Let's go back to our slide. Okay, so we've covered this entire slide. The iron atoms get photodisintegrated, The electrons combine with protons to make neutrons. Now, the whole thing that was roughly the size of the Earth is all of a sudden no longer able to support itself, and it's just freely falling. And it doesn't take long for it to fall all the way to the center. Now, what happens next? If the star, well, neutron degeneracy kicks in. It turns out that neutrons are fermions in the same way that electrons are. It's just that they can get much closer together before this degeneracy pressure kicks in. Well, guess what? This thing is in free fall, and it falls from something the size of the Earth down to something the size of a city. And when that happens, it's dense enough that neutron degeneracy pressure kicks in. Now the density is extraordinarily high, 10 to the 17 kilograms per cubic meter. The temperature is extraordinarily high, 10 billion Kelvin. And all of a sudden, the free-falling core, in less than a second, gets down to this fundamental limit, and then it stops at the bottom. And all of that stuff that was on top of that iron core, the silicon burning layer and the oxygen burning layer and the neon burning layer and the carbon layer, all of those layers are also in free fall. There's nothing supporting the center of the star anymore. And all of them are collapsing down on top of it. And all of a sudden at the center, it stops instantaneously. I do a demo, maybe I can show this in class, where I have a basketball and a tennis ball. And I put the basketball on top of the tennis ball, and I stand up on a table, and I drop both of them. If you've ever seen this happen, it's pretty dramatic. This is the effect of this collapse. The basketball represents the collapsing neutrons. The tennis ball represents all of the stuff on top of it. And you can probably guess, if you can't, you can YouTube it, or I'll post something or something. The basketball falling with the tennis ball, the basketball doesn't bounce much. The tennis ball takes all the momentum from the bouncing basketball, and the tennis ball gets shot almost to the ceiling of Newton 202. It's pretty spectacular. I wish you could have seen it. One of the sad things about distance learning. Anyway, that similar thing happens in the sun, in these massive stars. The collapsing core bounces, and all that energy from the bounce gets transferred to that stuff that was falling in on top of it. And you have a catastrophic failure of the star. The outgoing material from the bounce slams into the infalling material, and the outgoing material wins, and the star physically explodes from the inside out. You've got some diagrams down here that show you 10 milliseconds and 20 million milliseconds after the bang, not for any purposes other than to show you that this is not some nice, smooth, axisymmetric thing. It's very chaotic, it's very turbulent. But the whole thing will eventually be, all these arrows will be pointed in the opposite direction as the material from the inside bounces out dramatically, and the entire, at least outer parts of the star, explode from the inside out. It's a core collapse event. What do we call these things? Well, we call these things, I'm gonna write it down to be dramatic. We call these things, we call this thing a supernova. Let's break down this word. Obviously, super means really impressive and bright and impressive. Nova, I believe, is Latin for new star. And so there are things that are just novas. These things are when a normal, like white dwarf, accretes some material and you get some surface explosion on the outside. It can look like there's a new star in the sky. This freaked the ancient peoples out, right? They thought the heavens were perfect and unchanging, and anything that happens in the heavens that was changing was a cause for alarm. So anyway, these novae were a big deal. And so a star like a white dwarf could get extraordinarily bright for a short period of time, and this could recur actually. But that's a nova. A supernova is like that, except it's a much more energetic phenomenon. A much more energetic phenomenon. So why do we call it a supernova? Let's go back to our slides. We're almost done with this video. There we go. Why do we call it a supernova? Well, here it is, a picture of a supernova. Well, no, not this thing. This is a galaxy. This bright thing in the lower left-hand corner is a supernova that's gone off in this galaxy. The luminosity of what was already an extraordinary luminous star, a supergiant, increases for a short time by a factor of 100 million. It can, as you see in this picture, briefly outshine the entire galaxy in which it is embedded. These are extraordinarily bright and energetic events that can be seen literally across the universe. Okay, I'm going to stop there, and we will come back, and I will have a brief video that wraps up this up. I'll show you some supernova remnants, and we'll talk about a particular supernova that went off in the not so distant past. Stay tuned and see you in the next video.